In many biogeochemical models, we need to deal with processes such as abiotic precipitation or dissolution of minerals, or gas exchange between the water and the atmosphere. These processes are driven by the fact that the system is in a thermodynamic disequilibrium. How can we model this? We illustrate the approach on the dissolution of amorphous silica. This process is very important because it regulates the productivity by diatoms, which are microscopic algae responsible for a large chunk of primary productivity in oceans. First, we consider the forward reaction, which is the reaction where the solid phase silica reacts with water and forms silicic acid, which is the dissolved form of silica. We denote the concentration of the silicic acid by C and the area of the silica particle by A. Additionally, we assume that the volume in which the silica particle dissolves, V, is well mixed. We emphasize that mineral dissolution is a process that occurs at the mineral-water interface. Therefore, the amount of silica leaving the mineral per second will be proportional to the area of this interface A. Now, because this amount is entering the volume of water V, we convert the amount into a concentration by dividing it with the volume of water. Therefore, the rate of change in the silicic acid concentration will depend on the density of the reactive interface area A divided by V. In the last step, we introduce a rate constant Kd to ensure that the units are correct. Therefore, the rate of the forward reaction will be Kd multiplied with A over V. Now we turn our attention to the backward reaction, precipitation of silica. We will assume that this is an abiotic process. Because precipitation of silica on an existing mineral particle is again a surface reaction, the rate will depend on the area density as before. However, because the process describes the reaction of the silicic acid, the rate must be additionally dependent on the silicic acid concentration. As before, we finally introduce a rate constant Kp to ensure that the units are correct. Therefore, the rate of the backward reaction will be Kp multiplied with A over V and multiplied with C. In the last step, we consider both processes together. The mass balance equation describing the rate of change in the silicic acid concentration will have two terms, one describing the dissolution and the other one describing the precipitation. We can rewrite this expression by using some simple algebra. In this step, we denote the ratio between the forward and backward reaction as CEQ. We see that this parameter represents the equilibrium concentration of silicic acid, so the concentration where the rates of the forward and backward reactions are equal. Taking these results together, we see that the rate for the mineral dissolution precipitation reaction is proportional to the distance from the equilibrium concentration. Additionally, it is proportional to the area density of the reactive surface and the rate constant of the precipitation reaction. To verify that the mass balance is correct, we check the units. We have moles per cubic meter for the concentration differences, square meter per cubic meter for the A to V ratio, and meter per second for the rate constant, which together gives moles per cubic meter per second. This is the same as the unit for the rate of change in the concentration on the left-hand side of the equation, showing that the rate law is consistent. A similar approach can be applied to derive the rate law for the exchange of gases between the water column and the overlying atmosphere. We will not do it here in detail because the general principles are the same as for the process of mineral precipitation and dissolution discussed earlier. Instead, we only summarize the result using exchange of oxygen as an example. Specifically, the net rate of change in the concentration of the dissolved oxygen is proportional to the distance from the equilibrium concentration. Additionally, the ratio between the interface area and the volume of the well-mixed water column also plays a role. This ratio is equal to 1 over the height of the well-mixed water column. Finally, the rate is proportional to the rate constant in the units of meter per second. In the context of gas exchange, this rate constant is often called the piston velocity. We conclude that the processes describing partitioning of compounds between phases, the rate can be modeled by a function of the distance from equilibrium. Typically, we assume that the function is linear with respect to the difference between the concentration of the dissolved phase and the equilibrium concentration, called solubility. Solubility of minerals and gases in water can be looked up in thermodynamic tables. Here, as some additional information, we briefly explain how to calculate solubility from the first principles of physical chemistry. The process such as dissolution of amorphous silica in water can be written as a reaction where the solid amorphous silica reacts with liquid water and forms silicic acid. In a thermodynamic equilibrium, the concentration of the silicic acid, the molar fraction of the solid silica, and the molar fraction of water are related to the equilibrium constant K. Assuming that the silica and water are pure, the molar fraction of silica and water are approximately equal to 1. Therefore, silica solubility is directly equal to the equilibrium constant. Now, the equilibrium constant can be calculated from the standard Gibbs energy of the reaction, delta GR0, which in turn can be calculated from the standard molar Gibbs energy of formation of the products minus the reactants, as shown below. When this calculation is performed for water and amorphous silica, one obtains a value of about 1.4 millimoles per liter for silica in seawater and about 1.9 millimoles per liter for silica in pure water. Note that these values correspond to the standard conditions, so the pressure of 1 bar and temperature of 20 degrees Celsius. If you want to calculate the solubility at a different pressure or temperature, you must apply corrections derived from thermodynamics. The process such as degassing of molecular oxygen from water can be written as a reaction where the oxygen in the dissolved form becomes oxygen in the gas form. While the dissolved form of oxygen is described by a concentration in moles per liter, the gaseous form is described by a partial pressure in the units of Pascal or atmosphere. In a thermodynamic equilibrium, the concentration and partial pressure are related through Henry's law. Here, the so-called Henry's law constant is the equilibrium constant for the process described by the above reaction. Using Henry's law, it is therefore possible to calculate oxygen solubility in water for a given partial pressure of oxygen in the gas phase above the water. For example, for oxygen in contact with water with zero salinity and a temperature of 20 degrees Celsius, the value of the Henry's law constant is 770 liters times atmosphere per mole. Because Earth's atmosphere contains about 21% of oxygen, the partial pressure of oxygen at the sea level is about 0.21 atmosphere. Therefore, using the above formula, we calculate the solubility of oxygen in water at these conditions to be around 273 micromoles per liter.